Hi everybody, welcome to the colloquium. Today's speaker is Lauren Wesley, and let's say she comes from, but I'm not gonna lie, Harvard Smithsonian Center for Astrophysics. Okay, so Lauren earned her bachelor's degree in both in physics and astronomy at the University of Maryland, where her honors thesis focused on modeling nonlinear resonance interactions within the outer solar system planets. She started her graduate work in August of 2011 with Steve Kramer, who's sitting right there, at the Harvard Smithsonian Center for Astrophysics. And she completed a master's project in 2015 on one-dimensional modeling of coronal hole flux tubes, and has continued to look at the effects of turbulent heating of the solar wind. And as I understand, this is the kind of thing that she's going to be talking about today. She's also been interested in applying her science interest to teaching and active learning, as well as the development of science team board and card games, which is pretty cool. She's finishing her PhD in the coming spring, and in her own words, she's looking forward to the next step in her career. So, with no further ado, please.
Thank you. All right, I have to raise this back up again. So, as Rebecca said, I'm Lauren Woolsey. I just finished my 4th year at Harvard and am on track to graduate in May. And most of this talk is going to be basically the contents of my thesis so far. So there's going to be a lot of content, so it's going to be a general overview of those projects. So the structure of the talk is going to be sort of a short introduction to get everyone on the same page. So there's going to be a couple slides, just this early evidence of what the solar wind is, the corona, and then the motivation for this particular research. Then I'm going to get into the modeling efforts, which has been the primary focus of my thesis. And there's 2 main projects, one with one-dimensional modeling of flux tubes, and a second project that we just finished with 3-dimensional magnetohydrodynamics. I'm then going to get into some observational evidence, so an overview of prior research in the field, and then the study that we're working on right now, focusing on iris network jets, and then a short discussion. So the study of the sun in any form goes back millennia. So with solar eclipses, we were able to see the chromosphere because of that red color, and that light that we now know as the corona was able to be seen by anyone by the naked eye during a solar eclipse. We also have lots of observations from centuries and millennia ago of comets. And comets are really interesting because those tails point away from the sun. It was our first indication that there is some sort of outflow from the sun. It's not this static thing, but that there's this constant outflow away from the sun. And then, of course, there's countless effects on the Earth by the sun, where over time we, as a scientific community, started to realize that the sun is actually directly affecting life here on Earth. I'm also coming in a month where we've sort of been really focused on the magnetic field and the fast solar wind, the same kind of topics that I'll be talking about today. So several weeks ago, there was magnetic field in active regions, which I won't be focusing on, but magnetic field's a really big part of my thesis. And then just 2 weeks ago, there was a focus on heating of the fast solar wind. And so a lot of the content of that talk is very pertinent to what I will be talking about today, which is, of course, the magnetic influences on the solar wind, a study of turbulent heating. So like I mentioned, those comets, the tails of those comets, the first real work with them suggested that there was an outflow with speeds over 500 kilometers per second. So back in the 50s, we realized that there was this outflow that had significant speeds, but we didn't quite know what was causing it or why that was. Then Gene Parker's 1958 paper sort of gave us this first little insight that hydrodynamics, if you've got a isothermal spherically symmetric corona and you give it temperatures of over 1,000,000 degrees, then you can get this, this outflow. You can get these over 500 kilometer per second outflows if you've got a couple 1,000,000 degree corona. But then the sort of mystery moves then to, okay, well now we know why there's an outflow, but we don't know why there's the heating. So in order to really fully explain solar wind acceleration beyond a spherically symmetric isothermal corona, we need to identify the heating mechanisms. Those two main questions are really tied together, the acceleration and the heating. And all of the mechanisms that have been proposed can sort of be grouped into two main paradigms. One is if the theory is focusing on reconnection or the opening of coronal loops to be able to provide that heating and that acceleration. And the other paradigm is if you're focusing on waves, so mostly Alfvén waves and the turbulence created by those Alfvén waves. And of course, there are starting to become more and more theories that sort of combine both of these and where both factors are at play and very important. It's also possible to group these mechanisms based on the ratio of the photospheric driving, which is generally it's the motions of the foot points at the photosphere based on the granulation at the sun's surface. So the time scale for that and the Alfvén travel time. So if your proposed mechanism for heating where the driving is slow compared to the Alfvén travel time, then what's going to happen is it's going to be DC heating, where you're going to have to develop current sheets to be able to explain the heating. However, if that driving is really fast compared to the Alfvén travel time, then you can develop these magnetohydrodynamic waves. Sure. Right. So that's sort of a glossary, and it really does depend on the system that you're focusing on. So you're right. It's not a very clear answer, but it's basically the magnetic field and the densities that you're looking at, that Alfvén speed versus the distance that you're trying to model. So this talk in particular is going to focus entirely on sort of that wave and turbulence-driven paradigm, the AC heating by Alfvén waves. And we're looking only at flux tubes that are open to the heliosphere. So there's one foot point in the corona or in the photosphere, and that opens up to the heliosphere rather than a loop. So this diagram shows that on the left, at very small scales, at the granulation scale, you're getting the magnetic field coming up in between those granulation cells, and that's what's being moved around in the driving motions. Those magnetic fields sort of connect into this canopy at the supergranulation scale, where they're all coming in through the network of the supergranulation. And then at the very largest scales, at lowest order, the sun's magnetic field is very dipole-like, where you have lots of open field at the poles and the closed helmet streamers. Of course, all of that gets very complicated when you really look at the solar cycle, especially at solar maximum. But to lowest order, this is the sort of thing that we're thinking about. And I do want to make the note that while I'll be talking about MHD waves and Alfvén waves and the turbulent heating aspect of all of this, mechanisms in both paradigms may be contributing and may be working at different amounts in different regions. So it's still a very open question, but we can answer a lot of things about open flux tubes in regions where we often see fast wind. So the first paper that I'm going to sort of go over, which is the foundation of the next steps, is our parameter study of looking at turbulence-driven coronal heating and trying to improve the current use of empirical forecasting for the solar wind. So the primary goal is to understand the real relation between magnetic field and the magnetic field profiles in flux tubes and the solar wind properties coming out of these flux tubes. Because for a lot of forecasting, a lot of the community relies on the expansion factor that I have here from Wang and Sheely 1990, which is basically it boils down the entire magnetic field structure into a single ratio of the field strength at the source surface, which is at a distance of 2.5 solar radii from the sun's core, and the magnetic field at the photosphere. So it's normalized with this ratio of the heights out front, so that an expansion factor of 1 is radial expansion, the dashed black line in the top right. However, what I've drawn here is an open flux tube that, expands supraradially for part of its motion and then expands subradially, as you might call it, for other, where looking at that flux tube, your expansion factor would be 1, even though it's behaving very differently than an expansion factor that simply, or a flux tube that simply expands radially. So there's a lot that you can miss by just looking at the two heights and just the magnetic field at those two heights. And so this expansion factor is used often in WSA models where you predict the wind speed from this expansion factor with some simple analytical expression. This is one of the first ones that was used. Current use with the WSA model also includes a angle away from the nearest coronal hole. So it is more complex than what I've shown here. But the key part is, no matter how complex you make that analytical expression, if you're just using the expansion factor, then you've taken away all that other magnetic field information that could be happening between those two heights. So the whole goal of this talk, this particular part of the talk, this paper, is to try to understand if there's really a lot that we're missing by ignoring those middling heights, the magnetic field at those middle heights. So the first thing that we did to start our parameter study was to look at how the magnetic field changes over the solar cycle. So what I'm showing here is just examples of what potential field source surface extrapolation. So you have a magnetogram, so the magnetic field at the photosphere, and you extrapolate up, assuming potential field, which again is a simplification in itself, but it's giving us a starting point. And just looking at how the magnetic field changes throughout the solar cycle. So here what you can see is on the top row is speed over time. The middle line in these plots are at 500 kilometers per second. So most of the stuff below that line is considered slow wind, and stuff above it is considered fast wind. And what you'll notice is at solar minimum, the field strengths are lower than they are at solar maximum. And that's because what we're seeing here is measurements that are being made in the ecliptic. So during solar minimum, when you have a dipole field, all that fast wind and open field is coming out at the poles, and it's not getting to us in the ecliptic. And so what you're going to get is just the wind that's escaped from near the streamers, so the slower wind that has higher densities. And then on the right, you see at the start of the month's worth of data, we actually have some fast wind, because in solar maximum you can get equatorial coronal holes rather than just the large polar coronal holes. So you can get fast wind coming at us in the ecliptic. So we looked at several solar cycles worth of data and then compiled 672 models, where each one of these lines is a separate magnetic field profile for a single flux tube on its own. So as the magnetic field strength drops, the flux tube is expanding for flux conservation. And what I've drawn is this box here in the middle is showing you the ranges that were shown in these bottom left. So what we did was we, at different nodes, set a variety of strengths that you could have that basically covered all of the possible magnetic field structures that we would see over the solar cycle. And then we interpolated between those nodes to get all of the different possible combinations. And so some of these are unphysical because they're bordering on the extremes of something that we could see, but it's trying to get the full parameter study of anything that you could see in one study. So the work that we did started with ZEPHYR, which is a one-dimensional code, and the reference for it is listed at top, and it has the hydrodynamic conservation equations. It also has radiative heating and cooling, as well as heat conduction, and it includes both Alfvén and acoustic waves, but what we were finding was that the Alfvén waves were providing the bulk of the heating that we cared about. So what ZEPHYR does is it solves for a self-consistent and, again, one-dimensional, so everything is just in terms of the height above the photosphere, a steady-state solution for the bulk properties of the solar wind. So the sort of things that you would get would be the temperature is a function of height, and the density is a function of height, and the wind speed. From just giving it these magnetic field profiles and the spectrum of the waves at the photosphere, which comes from observations. So by keeping that same sort of driving motion at the base and using all 672 different runs through ZEPHYR, we were able to compile statistical information about how all of these different magnetic field structures might affect the properties. So one thing that we looked at was how the heating specifically depends on the magnetic field. So if we look at this phenomenological heating rate at the top here, from a large body of work of turbulence simulations and models, it can be shown that you can write the heating rate as the density, and then at the top we have the Alfvén variables, which are a sort of stand-in for the Alfvén waves coming in and going out. So the inward and outward Alfvén waves are the minus and plus Alfvén variables. And then that L perpendicular is the effective turbulence correlation length. So if we assume this correlation length is dependent on the magnetic field, and here to the minus 1/2, and for Alfvén waves at low heights, so in the low corona or in the chromosphere, you can show that the Alfvén variables are actually proportional to the densities of the minus 1/4. And then in the thin flux tube, a bit before the flux tube has had a chance to expand in the high corona, you can also show that the magnetic field is proportional to the density of the 1/2. So if you plug all of that in and you throw everything in and then see what you have left, what you have is that the heating of the Alfvén, or the heating in the flux tube, is actually directly proportional to the magnetic field strength. So if you have stronger magnetic fields, you're going to have more heating, as long as you're in these low heights thin flux tube limit. And when we look on the right here, we have a plot of the Alfvén wave heating rate as a function of magnetic field strength, shown for all 670 models at a low height of 1/4 of a solar radius above the photosphere. So we've drawn the line for this power law with exponent of 1, and it actually does a pretty good job. So all of these assumptions, which we weren't putting into the model, are actually a good way to sort of look at the fact that heating really cares about the magnetic field, not just at these two heights, not at the photosphere and at the source surface, but also in between. The heating is really caring about what's happening at these middling heights. In addition, we looked at the expansion factor that we talked about. So can you really give this simple expression for any kind of line through all of these models for expansion factor to give you wind speed? And the simple answer is you can't really. So what we've shown here is all of the models. Wind speed is on the y-axis and expansion factor is on the x-axis, and there is a large amount of spread. So that original equation that I gave you a few slides ago from Argy and Pizzo 2000 is the red dashed line. There's also another analytical expression that was fit for a set of models from Cranmer et al. 2013. And the key here is that there is really no simple line you can draw through all of those models. There's a lot more that the magnetic field is doing than you can just get from this expansion factor. But we do see that the higher expansion factor, so if you're expanding more quickly, then you have lower wind speeds. And this sort of simple idea is something that has been seen in observations. So it's something that we do still get out of our models, but you can't draw this simple line. we wanted to look at other correlations to see if there were any tight correlations you could make with the magnetic field properties instead of just the wind speed correlation. So on the left, we have the temperature at 1 AU and the outflow speed at 1 AU for all of our models. So the red outline is a data set of several years worth of data, and that's just sort of a contour. So all of that data is in that contour. And we really do fill in the right amount of spread for the temperatures at those outflow speeds that are typical of the fast solar wind, so the 600 to 800 kilometers per second. The higher wind speeds that you're getting to be 1,000 and higher, while that may be something that could occur in a flux tube standing alone, as it makes its way to Earth, it's going to be interacting with the streams next to it. And so even those high speeds would get smeared out. So it's not unusual for us that the Omni data set wouldn't stretch out that far. And the green line comes from the proton temperatures, a correlation found in observations by Elliott et al. 2012, which also goes right through the middle of what we're looking at. So we were happy with both of those. Also on the right here, we have, if we wanted to try to get something out of this simple, just looking at the magnetic field strength at one height, could we get something that is actually a really strong correlation? And we can. So even though that outflow speed has a big spread, on the x-axis here, we have the magnetic field strength at the source surface, so 1/2 of that ratio for the expansion factor. And on the top, we have the maximum temperature. So that's a very tight correlation. And at the bottom, we have the temperature at 1 AU, which again is a pretty strong correlation too. And if you can see, it's kind of hard. All of these dots are color-coded. They're binned by every 200 kilometers per second. So the very lowest points here are the red points that have lower than 500 kilometers per second. And if you look for each bin, there's actually a much stronger tight correlation in that bin than when you look at everything as a whole. So you really can get a strong correlation between the temperature and the magnetic field, which actually helped us with creating a standalone code called TEMPEST. So TEMPEST was also in this same work, and I published a secondary paper on its uses in the classroom, and it's on GitHub if you're interested. And the physics is basically a boiled down version of what ZEPHYR does in an attempt to make it something that you could use for solar wind predictions. So ZEPHYR is computationally intensive compared to this simple WSA, plug in the expansion factor into an expression. We wanted to see if there was something that was also fairly simple and fast to run that could be used for the same purposes. So TEMPEST uses the momentum conservation equation, so that's the modified Parker equation part of the acronym, and it uses Alfvén wave action conservation and the temperature profile. So the fact that we had those really strong temperature correlations is actually the reason that we can use TEMPEST. So again, it's solving for a self-consistent, one-dimensional steady-state solution with that magnetic field as its only output. So what we're doing is we're solving this code at the top. And so at the beginning, we set so with Parker, his original work was there was a critical point where you went from the subsonic to supersonic for the critical point. So our starting point was setting this critical point to be where the wind speed went through the sound speed, and then we'll add Alfvén waves onto that. So we find the point where that's true, and then we solve for the slope at that point and integrate outwards. Once we have this initial solution, we can actually add in the waves because we needed that initial guess for the speed so that we could give an initial guess for the density, and then we iterate through undercorrection, getting to a steady state. Now, folded into all of this is that we don't have the temperature profiles because we're not doing the radiative heating and cooling, we're not doing the heat conduction, But that's where ZEPHYR is helping us out. So the fact that we have almost 700 models with really strong correlations lets us define nodes in the temperature profile and find where the correlation is strongest with the magnetic field and what the expected magnetic field or what the expected temperature from that magnetic field is. So in the top we have the results from ZEPHYR that had all of the physics included. And then on top of that we have the TEMPEST temperature profiles. So it's about the same spread, and if you look at any particular model, they look very similar. And at the bottom we show where those nodes track back to. So for each of the defined temperature nodes, we found where the magnetic field had the strongest correlation with it, and then used those to define these temperature profiles. And all of this is in the paper in great detail in the appendix. We also followed a similar process for the reflection coefficient for the waves. So for the Alfvén waves, rather than guess at a very simple reflection coefficient, we actually used the same process to get strong correlations to be able to use Alfvén wave action conservation without the full physics. And what we found is that TEMPEST, while it makes simplifying assumptions, so it's not going to be the exact same answer, there's actually very strong agreement between TEMPEST and ZEPHYR. So these blue lines at the top right are when you have TEMPEST and so TEMPEST is on the y-axis and the ZEPHYR speeds are on the x-axis. So if it was all the same physics and all the same coding and just a different name, everything would lie along this black line. And you see that everything clusters very tightly around it. The interesting thing about TEMPEST is because we're doing this step where we have the temperature profiles based on the Alfvén wave heating before we add the waves, we actually get to disentangle the fact that the waves are heating the corona, so it's increasing the gas pressure, but they're also providing their own wave pressure. So back when we had this step before we added those waves, before we had the full expression for the where that critical point is, where that it's no longer subsonic and it's not just subalfvénic, it's this expression combining the two. Before that, we actually have an example of if there were heating but no additional wave pressure, the speeds we would expect, and they're much lower. So there is actually two main ways in which Alfvén waves are contributing to the solar wind acceleration, which is a key point that was something that we were very excited about. And in addition, this bottom plot is just, rather than comparing TEMPEST and ZEPHYR, it's comparing, again, that expansion factor in ZEPHYR, showing that the spread is much wider. So TEMPEST is doing a better job as a simplifying way of looking at things than even the WSA model still does. Okay, so the goal of that previous study was to better understand how the magnetic field affects the solar wind properties, starting from a very simple expansion factor and trying to move to something that could be used so it's still simple and computationally cheap, but there's more physics involved. The next step that we wanted to do was to expand that further. So rather than just having everything as a function of height, we wanted to have 3 dimensions. We wanted to have the cross-section of the flux tube because the Alfvén waves are actually moving about in those dimensions. And we wanted to include time dependence. So ZEPHYR solves everything in a time-steady way so that it, again, isn't too computationally intensive. But here, we're going to be using braid. And braid has been used before by Van Balahoyen et al. 2011, as well as several papers by Asghari Targi et al., focusing on heating in coronal loops. And this is the first time that we're using braid on open flux tubes. So the 3 models that we wanted to use, because again, braid is much more computationally intensive, were some sort of key structures that you would see in the corona over the solar cycle. So rather than 672 profiles that could or could not be found, we chose 3 that were very indicative of things that we actually do see all the time. So while the colors are hard to see, The solid line is a profile for a polar coronal hole. So one of these open flux tubes that is sort of in the middle of this polar coronal hole, and you expect very fast wind, very simple, out of it. The dashed line is an equatorial streamer, so it's an open flux tube that's neighboring an equatorial streamer, and it's the kind of wind that you would see throughout the solar cycle in the equatorial plane, so the things that we get in observations. And then the dashed dotted line, the red one, is an open flux tube that's right near a very strong magnetic field active region. So it behaves similarly to the equatorial streamer further out, but it actually has a much stronger magnetic field at low heights because it's next to this active region. So the results here are coming from ZEPHYR. So before we go into BRAID, we wanted to make sure that we knew what we were comparing it to. And so the outflow speeds are shown in the middle. And as expected, the polar coronal hole has the highest speeds, and the other two lag behind it. And then the temperature profiles as well. So the polar coronal hole and equatorial streamer have transition regions at 0.01 solar radii above the photosphere, and the active region has a transition region that's a little higher up. So this driving by Alfvén waves we look at more in detail in BRAID. So again, this simple idea of the foot point motions being driven by granulation is still at play. But what we're doing now to be able to fully simulate that is there's a white noise time stream passed through a Gaussian frequency filter that sort of takes out any fluctuations shorter than the correlation time of 60 seconds. And that comes from observations that I'll get back to in the observation section. And also from observations, we normalized these to an RMS velocity of 1.5 kilometers per second. And then we split them between these two modes. So this is showing vorticity as a function of simulation time and just showing that sort of random walk driving. So the first thing that we did after we had these three runs is before we started to look at the time dependence itself, just the fact that we have 3 dimensions, how does that compare to what ZEPHYR was giving us with the with 1 dimension? So on the left, we have the Alsacer variables. So again, this is that stand-in for the incoming and outgoing Alfvén waves. And in dark blue, we have what we're getting out of BRAID, and in light blue, that's what we're getting out of ZEPHYR. And so they agree very well. On the right, we have the magnetic and velocity fluctuations, both in speed units, velocity units. And again, the dark lines are what we're getting out of BRAID, and ZEPHYR enforced equipartition between the kinetic and magnetic energies. So there's only 1 line there, but it passes through roughly the middle of those at those higher heights. So it's doing a pretty good job. The fact that they agree means that ZEPHYR is giving us a lot of physically important and accurate information, and that BRAID agrees with it. We also looked at the heating rate coming out of BRAID. So again, we have these 3 dimensions. We wanted to make sure that it sort of agrees with what we've been doing before. So we compare it to that same phenomenological expression that I showed earlier. And so if they agreed perfectly, they would be at a ratio of 1, which is that solid line across. And they sort of span around that, but all within an order of magnitude. And in the paper, we talk about looking at this with different efficiency factors for turbulence in front of that phenomenological expression. But the key part is what we've been doing right now is averaging over time, but we really wanted to see what time dependence would give us. And that heating rate is very bursty. So at the top, we have the energy density volume averaged over the corona in our models as a function of simulation time. And so it's very, very bursty and very varied. And at the bottom, we have the coronal heating rate, which has these spikes. And we wanted to sort of understand the implications of this particular aspect of it. So one of the things we did was we took this volume averaged heating rate that we just looked at and a somewhat simple conductive scaling relation. So the temperature is proportional to the heating rate to the 2/7 power. And so at each time step, we sort of look at the temperature that you would expect from that current heating rate. And so we build up this probability density, which is we can liken to a differential emission measure, and compare both its centroid and the width to measurements of DEMs of observations of coronal loops. And so on the right here, the diamonds show the observations of coronal loops for Schmelz et al. 2014. On the left, we have the width of that DEM, and on the x-axis, we have that central temperature. And so all three of our models fall in this same range at somewhat lower temperatures because the heating isn't as significant when you don't have two sources of Alfvén waves that can very strongly interact at the top of loops. But we still fall exactly where you would expect from this same kind of multi-thermal plasma idea. And the spectrums themselves, the fluctuations themselves, now we have a power spectra because we have this time dependence. And the high frequency part tends to follow a power law. And the key point in this left diagram is that the dashed line is the input spectrum of those driving motions. And you add power at these high frequencies throughout the course of the simulation. The two different colors are blue is the spectrum at the end of the simulation at the photosphere, and in red is the spectrum at the end of the simulation for the top of the grid. And so we show these power law exponents, and we go into this in the paper in more detail, but the value of n may be able to constrain the models of anisotropic turbulence. So that is something that we found very interesting. And back to this sort of bursty heating rate, it's very nanoflare-like in nature. So Asghari Targhi et al. In 2013, also using braid, looked at closed loops, and they did a box capturing analysis. And so you can estimate the energy lost by dissipative heating if you look at that heating rate as a function of height and time in boxes of a finite width in simulation time and height in the flux tube. And so if you count up all of these boxes and the energy contained within them, they found sort of this peak at 10 to the 23rd ergs with a pretty low standard deviation. And we found that, again, because we don't have loops where we have two strong sources of Alfvén waves that are connecting, and we just have the reflecting back down to give us the counter-propagating Alfvén waves, we found a lower central energy, but we do have a tail that reaches even past what they found. So most of this is in the picoflare energy range, and we get into the nanoflare range. And another thing that we wanted to do was this sort of spawned a secondary paper on the variability of the heating rate and how it affects the transition region if you consider mode coupling. So braid, we have these Alfvén fluctuations, so the perpendicular fluctuations, and we can mode couple them to compressive waves, and so now we have parallel fluctuations, which can lead to shocks, which can give us these sort of wave pressure type variations, which can actually change the height of the transition region and give us some kind of apparent motion. And when you look at these pressure variations, if they're coming with enough with less time in between, you can actually get what looks like motion upward in height. And so on the right here, looking at how that transition region changed based on our heating rate variability, we have all of these points here, and many of them fall into the correct sort of time scales and vertical speeds seen in type 2 spicules and in the Iris network jets that I'll be getting to. And so this is sort of the big picture of the paper that we actually just submitted the referee response this afternoon. And now I want to get into what we're working on now is bringing in some observations to all of this. So we've been talking a lot of modeling, but there's a lot of observational evidence for Alfvén waves and for turbulent motion. And so this is sort of an overview of what we had up to around 2009, where we had these G-band bright points, and that's, again, I mentioned it before, but that's where the 60-second correlation time and the 1.5 kilometer per second RMS velocity were coming from, were these observations. And then we have observations all throughout the heliosphere to 1AU, where we have Helios and Ulysses data further out. And so some of the newer things that we've been adding on is, again, I keep mentioning these iris network jets. So on disk, one of the things that you can find is these intermittent small-scale jets that were really only being seen because we have these new the new wavelengths to be able to see that transition region chromospheric plasma, as well as the high enough resolution, because they are very small and very short-lived. So on the left, there's a dashed line in the upper left of that picture that highlights one of these jets, and there's the distance time plot on the top left, and there, in this particular paper, 64 jets in a particular iris observation were found, and their speeds were 100 to 200 kilometers per second, and they lived on the order of tens of seconds long. Off-limb, of course, we have a lot of observations as well. So there's a lot of alphanic motion, and so this is from a 2011 paper in Nature, where looking right above the limb, you can see a lot of these alphanic motions pretty much everywhere and all the time. And off the limb, when you add in comp, and looking at AIA, being able to use both at the same time, you actually get to see the different wave motions in the same structures. So with comp, you get the Doppler shift, where you can see the perpendicular fluctuations along the line of sight. And then with AIA, you can see these longitudinal oscillations. So you get to see this, what could be evidence of mode coupling, the same thing that we're that could possibly explain these jets from the braid numerical results. And so one of the latest papers using comp and AIA is showing how you really can see both of these different types of waves. So in the top left, and it's hard to see on the slide here, there are some dashed lines showing the Alfvén signatures in a distance time plot. And on the bottom, you have AIA 193 showing this, again, the other motions, the longitudinal motions. And so on the bottom, it's got 130 kilometers per second for those motions. And in this paper, they found the Alfvén phase speeds 830 kilometers per second with amplitudes on the order of 0.5 kilometers per second. So this brings me to our iris network jets. And so I just want to sort of overview what the plan is, because this is ongoing research. So this is where we're looking. It's an observation from last year that is right on the edge of a coronal hole, but it was a really nice large sit and stare observation where we have lots of time looking at the same location. And again, it's close to the limb because you're seeing these network jets in projected on top of the plasma behind it, so you do need to have it be far enough towards the limb so that they do have that angle. But it needs to be far from the limb in order to have reliable magnetic field measurements. So this was an observation we found that sort of hit that sweet spot in between. And so, like I said, this is a large sit and stare movie. And so this is just showing 300 time steps of a sit and stare that we have over 1,000 for. And so concentrate in the bottom left, you can see, so this patch here is a strong magnetic field network patch. And you can see some of these linear features in the movie. And again, these are very hard to find, so that looped through. These are very hard to find with the human eye, because as soon as you stop the image, any jet motions you see start to blur out. So let me get back to this. So what we're going to be doing is we're going to be comparing the magnetic field seen by HMI with SDO and trying to get an idea if there's some sort of threshold, either in the net flux or in the flux imbalance, that is conducive to producing these network jets. So on the left we have the line of sight magnetic field, and on the right we have this same region in a different color scheme, where again the regions of strong magnetic field are where we're seeing a lot of these jets come out of. And so this is just sort of the overview of the magnetic field that we're finding in these areas. So what we did was we broke up this region into grid cells of 5 arc seconds by 5 arc seconds, and calculated the net flux in these grid cells and the flux imbalance. And so ignoring the units for now, this region is mostly negative polarity, so it's a very unipolar region, and the regions of strong flux imbalance have very strong magnetic field strengths. And so we're going to be comparing these two properties as well as other magnetic field properties to some sort of explanation of the jet productivity amount. And so what we've been finding so far is everything is very promising. So we're looking forward to how this turns out. So in summary, our one-dimensional modeling, that first project that I talked about, shows that the magnetic field really does have a more complex relationship than any simple analytical expression can give you. And when we move on to three-dimensional modeling, we're finding that when you time average it, it matches that one-dimensional modeling. So the 1D models are still very useful for a lot of things. Once you look at the time dependence, you're getting a lot more information out of it. So the fluctuations in those models were showing us this power law that may really help us understand the theoretical models of anisotropic turbulence. And the bursty nature of that coronal heating found in braid really can tell us a lot of things. So it matches with those observed the multithermal nature of the coronal loop observations, as well as our box capturing analysis is on par with picoflare and nanoflare energies. In the mode coupling of Alfvén waves, that secondary paper can really help us to connect the braid results with observations of things like the iris network jets, which is what we're working on now. So thank you very much, and I'm happy to answer any questions.
I didn't understand the word about just the last part about the imbalance in the magnetic field distance. Could you? Yeah, the first. So, what I understood, and maybe I'm wrong, is that you are studying or you observe these network jets. Mm-hmm. How is the magnetic field?
Exactly. So we're looking if there's some minimum flux imbalance that you must have in order to have these network jets, just trying to put better constraints on the mechanisms for generating these network jets. And so either finding some kind of correlation with the imbalance, like is there a minimum imbalance you need, or do you get more jets if it's more imbalance, things like that.
But what do you call that imbalance? What is imbalance?
Oh, right. So it's the net flux. So adding up all of the magnetic field strengths with their signs over the absolute amount of flux.
I also understand. But my question is, what is the region that you define? What do you consider it has to be on balance or unbalanced? My question is, you're observing a patch. Mm-hmm. It's clearly a black patch in this color.
Right.
So it's going to be unbalanced, for sure.
Right.
You are not considering the other part.
Well, so what we're doing is we're looking at the entire region and trying to classify.
Yeah, but my complaint is that you are observing in the entire region that you have for an iris, mm-hmm. but not in the entire magnetic region. So it might be deeper. My point is that this patch probably is related with another reverse polarity patch that is not in the field of view of iris.
Right. No, that's very true.
It's going to be unbalanced.
Right. Yeah.
A small scale, not
Yeah,
the
but
these are mostly coronal holes, so they're mostly unipolar on the largest scales.
but a small scale is still mixed polarity, right?
yes, of course, but you are, I mean, you go to this black patch, it's going to be flat. It's going to be flat, right? It's going to be absolutely unbalanced in a way.
Yeah.
But how unbalanced? Because
Exactly. Maybe if you have mixed polarities, if you have more like white and kind of sub-region, then there's more reconnection.
My question would be, if there is another patch with the reverse polarity, are you observing also the network jets? That question.
right. So this particular region, because it's not in an active region where you definitely have really strong in both, we're really only seeing the unipolar region. Yep.
But it's still important to see if there's little parasitic bits of the opposite polarity. Because if the jets always are associated with those parasitic polarities, then it favors a reconnection model
Right.
for the jets. But if not, then this wave coupling might be the more favorable. It's really uniform.
My only comment about this is that HMI is probably not the best instrument that you can.
I agree. I agree. It's a starting point. And actually, another reason we picked this patch is because it was a coordinated observation with Hinode. Yeah, SOT. Yeah. Well, we don't have it, but they were looking there at the time.
But how long
Does it exist?
Yeah, it does. I just haven't downloaded and looked at it yet.
Should be super easy to get.
Yeah. Mm-hmm.
How fast are these events, these jets?
So they exist for tens of seconds, and so for Iris, it's 2 to 3 frames that some of the shorter ones.
So you are thinking an NFI or speed is not, doesn't make sense at all.
Depends what kind of observation it is.
Yeah, we should definitely talk offline.
I'm a bit of an outsider in this area, but is the heating occurring in the collisional or collisional regime of the plasma?
Both.
So how does it get from one fluid Alfvén waves into the plasma and the collisional?
That is a good question. So the dissipation mechanisms is not something that we were modeling. We just assumed that with this turbulent cascade, once it got down to that dispersion scale, that it would disperse. We weren't modeling any particular mechanism for that.
So the idea is that a cascade gets it into the dispersive Alfvén wave.
Right. But that's still a completely open question, what mechanism is doing that. You're right. Yeah.